So, the next type of flow meter uses what's called the calorific effect. Basically, it boils down to this. You're driving along and you get hot, you haven't got air conditioning, what do? You got it. You open the window. When you open the window, if you open the window and you stick your hand out, your hand gets cooled down. The faster you go, the more it gets cooled down. That's the calorific effect. Basically, the faster the fluid is passing, the more cooling there is. In actual fact, if you could stick your hand out into water, say you're on a boat, if you're on a boat moving along, if you hold your hand out, it cools down. But if you put your hand in the water, it cools down even more. Because what the calorific effect actually measures is the more mass of fluid that's moving past, the more cooling there is. Of course, doing that in the Northern Territory, you'll probably get your hand bitten off. But that's besides the point. The more mass that moves past, the more fluid mass moving past, the more cooling there is. So the calorific method is simply a method of measuring the mass flowing past. And it measures the mass flowing past by measuring how much cooling occurs. Generally speaking, we have a couple of probes, and one of the probes is heated and one of the probes isn't. This is to allow for the fact that the liquid just might be cold. So we allow for that, and then the more cooling that occurs on the heated probe, the more mass has moved past. So it gives us a mass flow in kilograms per minute. Here's a couple of calorific sensors that you can buy. There's an insertion one, and the other one, the one on the right, you'll probably all got these. The one on the right is an airflow sensor from a car fuel injection system. You see, they've always had fuel injection. One of the first petrol motors ever built used fuel injection. We've always had fuel injection. But up until recently, all cars were fitted with carburetors. The reason why all cars are fitted with fuel injection now is because in order for fuel injection to work well, we need to balance the fuel addition to the airflow in. We couldn't do that up until something like the 1990s. In the 1990s, we started making accurate, cheap airflow sensors. And they use the calorific effect. And these accurate, cheap airflow sensors are now what's fitted in the fuel injection system of your cars. And because we can accurately measure the airflow, we can accurately dose the fuel in. And so we have fuel injection systems which are very accurate. So that's something that's come about only in probably the last 20 years, that we've increased, because we can now accurately and cheaply measure airflow, we can now have good fuel injection in every car. The next type of flow meter is our fallback flow meter. This is a displacement flow meter. Basically what we have is some type of displacer, a ball bearing or something, in a pipe. The fluid comes in at the bottom and leaves through the top. As the fluid flows, the little displacer gets pushed upwards. Sometimes they're called rotameters, because this little thing is designed to rotate slowly. Sometimes you've got a little ball bearing in there which just raises up. But basically they're displacement flow meters. These are our absolute fallback. If you've installed a big expensive flow meter and for some reason it dies, a lightning strike or something, As long as you've got one of these and a hand valve, you can carry on running. Because if you have one of these and a texter and a hand valve and an operator, you can keep the plant running. You just say to the operator, look, there's the texter line, just open and close the hand valve to keep the displacer in the right place. It's a pretty low-tech control system, but if you're running at, say, $10,000 an hour downtime, then everybody's going to go along with this. The only problem with the displacement type flow meter, there's two problems, and both of them come from the fact that it uses a transparent glass tube. Firstly, it's made of glass. If you work in a factory or a mine site, then you know that anything made of glass, the forklift truck drivers will hunt it down and kill it. That's their main purpose in life, is to find glass instruments and break them. So you have to try and protect this from the forklift truck drivers, because they will find it. Strange enough, it doesn't really matter what you put in. You could put Claymore mines in place, and the forklift truck drivers will still manage to break the damn thing. So that's something to bear in mind. The second thing to bear in mind is, if you've got drinking water going through this pipe, then it will fur up and go green and fuzzy. And that's because drinking water contains lots of other things. So that's a couple of things to bear in mind with this displacer. Oh, I just realized I'd forgotten something. I'll just go back a step to the calorific, if I may. Just looking at the calorific quickly then. Will it work with gases? Yes, it will. It actually works really well. Will it work with water? Absolutely it will. Will it work with oil? Yep. I should mention it's not specially accurate. Will it work with liquid with gas in it? Yes, it will. Because in fact it works pretty well because it tells you the mass going past. Will it work well with sewage? Not so specially well, eh? Something to bear in mind. Okay, looking at the displacement meter, will it work with gases? Yep, it will. Will it work with water? Yes, it will. Oil? Bear in mind, it's a glass tube, so if that breaks, it could be a serious disaster. So it will work with oil, but would you choose to use it with oil? Maybe not. What about then liquid with gases in it? It's a bit of a yes, it will, no, it won't. You're right in choosing. It's hard to say. If there's too many air bubbles in there, it's probably going to block up. It's probably going to airlock sooner or later. Sewage? Not really much of a chance of it working with sewage. You're going to get a bit of toilet paper wrapped around that displacer and it's going to be all over. Right. Another type of fluid flow we often need to measure is open channel flow. Open channel flow is normally outlets from tailing beds, outlets from settling beds, outlets from water treatment plants. We have to pay for stuff to go out. So we need to know how much is going out so that we know how much we pay. The way we measure this is by using a thing called a flume. A flume is a piece of calibrated riverbed. And basically, you buy your flume, comes on the back of a truck, you dig a big trench, you install your flume, and then you channel your river through the flume. Because it's a calibrated riverbed, the higher the stuff rises in the flume, the more the flow. We generally use an ultrasonic level detector to detect the level, because ultrasonic is non-contacting, it's nice and simple. So we detect the level using an ultrasonic level sensor, and Bob's your uncle, we know what the flow is. Nice simple way of doing open channel flow. Now here's a couple of examples of what can go wrong with an install. This is a pipe showing an obstruction in that pipe. So we've got a small obstruction in the pipe, and the colours represent velocity profiles. Now what's happening is we're flowing from left to right, and that small obstruction is completely, as you can see, messing up the velocity profile. For 4 pipe diameters downhill, in fact, that small obstruction in the pipe is completely messing up the velocity profile for 20 pipe diameters downstream. So any sort of obstruction in the pipe will completely mess up the velocity profile, and virtually all the flow meters, except for the Coriolis flow meter, will measure an incorrect flow. The sort of obstructions in the pipe I'm talking about are things like this. You see that gasket? Gasket is just slightly off center. There you've got a gasket which is slightly off center. That gasket would have cost 50 cents. There you've got a flow meter which would have cost maybe $10,000. That $10,000 flow meter is now useless because of that gasket. It will measure completely wrong. So that's the sort of thing that can mess up our flow meter. Other things that people do. Here we've got a flow meter which has been installed in a pipe. Now, the top picture was showing the flow meter installed in a pipe. This thing here, this is a thing called a rotating basket. Basically, it's a big rotating piece of machinery, and you better believe that's seriously messing up the flow pattern. The reason why they've installed the flow meter here is because this is where the cable comes up. More often than not, we install the flow meter where the cable happens to end. Now, what makes this especially silly is if you look at the bottom diagram and you look, they had all of this pipe they could have installed that flow meter in, and they chose to install it here, right next to the rotating basket. This is not going to read correctly. Examples of how to badly install flow meters. What about this one? What do you reckon? Any elbows? The only reason I can see to install this flow meter like this is because it gives a convenient place to install the bucket. This flow meter is just a complete joke. There is no way this flow meter will read correctly. It just will not happen. Here, they've actually bolted the valve to the flange of the flow meter. Because, well, it's a flange. It's a convenient place to put a valve. And if you think we're looking at what, we should have 20 pipe diameters. Well, we haven't even got 1 pipe diameter. And they've installed the flow meter. The flow meter is installed just here. There is no way that flow meter is going to read. Now, all of these examples are from installs. These are things that have been done. They're not made up. These are installs. These are from the people who were called out to these things, and they took these photographs so we could all laugh at them. So this is how we're installing. Let's look at another one. Here we've got a flow meter installed, and well, a little bit difficult to read the display on that one, isn't it? So these are flow meters. This is where a flow meter goes wrong. A modern flow meter is accurate. If it's not accurate, it's because of the plumbing. It's because there's air bubbles in there, there's sludge in the bottom, the pipe's stirring up, or there's an elbow on there, or there's a gasket out of place, or there's some obstruction in the pipework. What goes wrong with a modern flow meter is not the flow meter. What goes wrong with a modern flow meter is the plumbing. And by the way, looking at this example, they've got a reducer right here, which is also going to totally screw the thing up.